graph all asymptotes for the following rational function. So here we are given the function f of x is equal to x squared plus 2x minus 1, all divided by x plus 3. So the very first thing that we want to do when we're graphing asymptotes or graphing a rational function is to check to see if this function can be simplified any further. And we do this by factoring the numerator and denominator separately. So here we go. We are given f of x. And now we have a quadratic in the numerator, x squared plus 2x minus 1. And a binomial in the denominator, x plus 3. So our denominator can't be simplified any further. There's no common factors, so that's all set. Can we factor the numerator? No, we're stuck here. So f of x is simplified. Perfect. So now that we have verified that this rational function is as simplified as it can be, we're ready to go ahead and start finding the asymptotes. So our first asymptote is the vertical asymptote. Now I want you to recall that vertical asymptotes are the zeros of the denominator. So to find the vertical asymptotes for this given rational function, we are going to set the denominator equal to 0 and solve for x. So we have our denominator is x plus 3 is equal to 0, and then solving for x, we subtract 3 from both sides of the equation. So we see 3 minus 3 cancels out to 0, leaving us with a vertical asymptote at x equals negative 3. So this is the vertical asymptote for our given rational function. So the next thing that we want to do is check this rational function for horizontal asymptotes. And again, I want you to recall that to identify the horizontal asymptotes, if any exist, we are going to compare the leading term in the numerator to the leading term in the denominator to see which degree is larger, smaller, or are they equivalent. So before we go ahead and scroll down so we have a little bit more room, or scroll up, let's identify those leading terms. So looking back up here at our given rational function, we can see that the leading term in the numerator is x squared. So this means that this leading term has a degree of 2. And in the denominator, we can see that the leading term is x. Or we can think about this as x to the first. So giving ourselves plenty of room, we are now ready to make conclusions about our horizontal asymptote. So again, we have identified that the degree in the numerator call this n, the degree in the numerator is 2. And we have also identified that the degree in the denominator, which we're going to call m, is 1. So we can conclude here that therefore, since the degree in the numerator, 2, is greater than the degree in the denominator, 1, this tells us that there is no horizontal asymptote. So because the degree in the numerator is greater than the degree in the denominator, no horizontal asymptote exists. But we have a special case here. When the degree in the numerator is greater than the degree in the denominator, we have a slant asymptote. So in order to find the slant asymptote for this rational function, we are going to need to perform long division with polynomials. So we want to make sure that we are giving ourselves plenty of room here. So again, to find the slant asymptote, we're going to perform long division. So we have x squared plus 2x minus 1, and this is all divided by x plus 3. So we know from way back in algebra that this fraction can be written or rewritten in a long division form. This is telling us that we are dividing the numerator, x squared plus 2x minus 1. we are dividing this numerator by x plus 3. Beautiful. Now, when we're performing long division with polynomials, we just want to think about the first term of our divisor. So we're asking ourselves here, x times what will give me x squared? Well, we know x times x equals x squared. So there we go, our first term. So again, x times x gives us x squared. X times 3 will give us plus 3x. Now be careful here, we're performing long division, so this means that we are subtracting this term. So this negative needs to be distributed through to both terms here. So we can add little negatives in front of or inside our binomial. So we have x squared minus x squared, those terms cancel each other out to 0. And then we have 2x minus 3x leaves us with a minus x. Beautiful. We'll bring our next term down. So we now have negative x minus 1. And again, we're asking ourselves, x times what is going to give us minus x? Well, we know x times negative 1 equals minus x. And we can check. We have minus 1 times x gives us minus x. Minus 1 times 3 gives us a minus 3. And again, be careful here. Because we're performing long division, we are subtracting these terms. So we'll take this negative and distribute it through to both terms here. So negative times a negative will give us a positive x. Negative times a negative gives us a positive 3. And now we're ready to simplify. So I have minus x plus x. These terms will cancel each other right out. And then we have minus 1 plus 3 leaves us with 2. Beautiful. So if you want, we can think about this too as the remainder. So we have x minus 1 with a remainder of 2. And we know that this is the remainder because there's no more x's. So we can also rewrite this in a rational expression form. We can say that, again, we've taken this x squared plus 2x minus 1, all divided by x plus 3. And we've shown with this long division that this is equivalent to x minus 1 plus a remainder of 2 divided by the divisor x plus 3. So looking at this alternative form that we just found, we can see there's two distinct expressions here. Our first expression is a linear expression, or a diagonal line, or a slant, wink wink. And we've also got our rational function portion. So the linear portion of this simplification is our slant asymptote. And so we can say that therefore a slant or oblique asymptote exists at this diagonal line. So a slant asymptote exists at the diagonal line. Y is equal to x minus 1. Beautiful. Beautiful. So we are ready to begin sketching the graphs of these asymptotes on the xy plane. Now, before we do this, let's think about our slant asymptote. Now, again, our slant asymptote is a diagonal line. And in order to graph a line, we need at least 2 points on the line. So the easiest points to find on our diagonal line are going to be the x and y intercepts. Now we can already see the y-intercept of this diagonal line because our line is in slope-intercept form. So we have a y-intercept at b equals -1, or if we write this in its ordered pair form, we have x, y is equal to 0, -1. So there's 1 point on this line. And very similarly, we want to find the x-intercept. So we know the x-intercept is where the line crosses the x-axis. So letting y be 0, we have x minus 1 equals 0, which simplifies to x equals +1. And again, writing this in its ordered pair form, we have the ordered pair xy is equal to 1, 0. So we'll now use these two ordered pairs to sketch the slant asymptote. So here we go. So let's begin by sketching the vertical asymptote. Now recall, we found that we have a vertical asymptote at x equals -3. So where x is equal to -3, we are going to draw a dotted vertical line to represent this asymptote. Beautiful. So this is our vertical asymptote at the vertical line, x equals -3. And now to sketch our slant asymptote or our oblique asymptote, we begin by thinking about the intercepts. So we know we have a y-intercept at the ordered pair 0, -1, and an x-intercept at the ordered pair 1, 0. So using these two ordered pairs, we can now sketch a graph of our slant asymptote by drawing a dotted line passing through these 2 points. Beautiful. So this is our slant asymptote at the diagonal line. Y is equal to x minus 1. And there you have it. This is our beautiful final answer. And the graph of our rational function is going to exist in between these asymptotes.